Very happy to be here, and I thank KAIST and NIMS for inviting me to this interesting winter school. So I tried to prepare my talk to fit into the general theme of this program. And then I soon realized that this is a very broad program. I can only touch a very small corner of the things that we have talked about. So let's get started first. This picture, well, looks very good on my computer, but not so good on the big screen. Again, we'll look at morphogenesis problems. And so I remind you that the very first lecture given by Professor Li on this type of patterns. And fish also have patterns of this kind. And the starting point we learned from the first lecture is to look at the Gear-Manhart system. So here's the Gear-Manhart system. And it's a reaction diffusion system. I only wrote the steady state equations. And if you look at the equations carefully, you'll notice a little difference here. So I have put an extra term downstairs in the first equation, 1 plus kappa UP. And the others are all more or less similar to what we learned from the first lecture, except that we use more general exponents, PQ and RS, but that's not so important. You can take them to be 2, 1, 2, 0. So the important thing is this kappa. Now if kappa is equal to 0, and this problem is called a non-saturation Gear-Manhart system. And if kappa is positive, if you do have kappa here, then this system is nowadays called saturation Gear-Manhart system. And there's a big difference between these two cases. And in my talk, I will be mostly discussing the second case, the saturation case. There's a very large body of literature on the non-saturation case. And, but on the other hand, the saturation case is not very well studied. And there's an earlier paper by Manuel Del Pino on the radially symmetric solutions for this type of equations. And he looked at this system for one parameter range. And more recently, Sakamoto and Suzuki looked at the same equation in a slightly different parameter range. And in both papers, they found a radially symmetric solution with one interface. And here in this talk, actually, I will not solve this problem directly, but instead, I would just look at one particular parameter range. And then I will show that behind this system of PDEs, there is a simpler geometric problem. And that geometric problem by itself is quite interesting. And we can actually study that geometric problem first, find some interesting solutions. And we hope that these solutions match the pictures that we observed on these animal skins. So let me show you how we make a reduction from this PDE system to a geometric problem. And this is a formal argument. It's not mathematically rigorous, but it actually shows that quite clearly that there is a geometric problem behind this PDE system. So let me denote the nonlinearity of the first equation by f of UV, this one. And if you look at this nonlinearity carefully, treat it as an equation, treat it as a function of u with v being a parameter. And then this is a bistable function. Bistable means that it first comes down at 0 and then goes up and then it comes down again. And there is a particular value v0. And with this v0 here, with this particular v, then this bistable nonlinearity is balanced. Balanced in the sense that if you integrate this f from the smallest 0 to the largest 0, then the integral is equal to 0. So this v0 is actually quite important. Now let's look at the parameter range I will consider. Epsilon is going to be small. Remember that epsilon squared is the diffusion coefficient of the first equation. D, the diffusion coefficient of the second equation, is going to be large in the sense that D is a constant divided by epsilon. So this parameter range is exactly the same as the one considered by Sakamoto and Suzuki. It's a little bit different from the Delpino's case. Delpino looked at a fixed D, not a fixed large, but not as large as 1 over epsilon. So the hope is that we can actually find a subset of the domain D, subset called E, such that the solution, the U component of the solution, the activator, is going to be close to a constant inside this set and close to 0 outside this set. So this U is going to develop a rather simple profile. It's like a characteristic function of a set. And to describe the behavior of this U part near the boundary of the set, let's recall a function Q. Q is the so-called traveling wave solution of this second order ODE. So here you have Q cosine plus a constant times Q cosine plus f of Q and S, where S is a parameter, and this is normally called the traveling wave problem because we impose that at negative infinity Q is 0, at positive infinity Q is the largest 0 of F. And because for general S, this F is not necessarily balanced, so you have to add a constant times Q cosine here for this equation to hold. And this is called a traveling wave equation, but in our case, the cosine is not time. So cosine is actually a variable in space. But anyway, because of the convention that we still call this a traveling wave equation. And in this problem, the constant C is unknown. You really have to solve the equation for both Q and C of S. And this constant depends on S. Now, we need this Q. And then we assume that near the boundary of this set E, U is like Q. And to be more precise, we let d of x be the signed distance from a point x to the boundary, and positive if your point is inside the set, negative if the point is outside. And then we assume, well, we hope approximately that u is equal to q of d of x over epsilon, cosine replaced by this scaled distance from the interface, and a parameter s to be determined. So we hope that this guy is going to be close to a solution, well, u component of solution. And we insert this quantity into the first equation of the Gear-Manhart system. And the first equation says that while you will have the Laplacian of this u, which will give you this term, and then also this term after you do the Laplacian, and then this is the nonlinearity, it has to be 0. And then if you just look at the left side on the boundary of the set, and you know that the gradient of d actually is equal to 1. So this term becomes 1. And the second term, Laplacian of d, becomes the mean curvature of the boundary. So we do this in 3 dimensions. The spaces are 3. And then this equation simplifies to this, and you compare this to the traveling wave equation. And you find that in order for this to hold, your epsilon h, this term here, has to be equal to the speed of the traveling wave, c of s. And your f of, well, here your v has to be equal to the parameter s on the boundary of the set. So, well, that's good. And then you go on to look at v more closely. Now, if you remember the first lecture, there was one game people play. People assume that v is a constant. And then the Gear-Manhart system becomes a single equation, and then there's a whole big story. So here we have to do a little bit more. Just taking v to be a constant is not enough. So we assume that v has a, well, it's unlike U, V actually is more smooth. So V has an expansion like this. The leading term is still constant, V0. But then there's a higher order term, epsilon times W. So we take this to be V, assume that V has this expansion. And then, of course, C of S is C of V, and we expand this speed at V, and we write down this two terms of the theta expansion. And we know that V0 is the parameter that makes the function balanced. So at V0, the speed of this traveling wave is equal to 0. Right? In the balanced case, you have a standing wave. So C of V0 is equal to 0. Therefore, Cs now is approximately epsilon times C prime at V0 W. And you compare this to the other side, epsilon H. You find that H, the mean curvature, has to be equal to C prime at V0 times W. So that's an interesting equation, a good equation, but it's not enough because there are too many variables than equations. There's a set, a boundary of E to be determined, and then there's also this W. So we have to find another equation for W, and for that, we take this V and insert it into the second equation of the Gear-Meinhardt system. Now you put it into the second equation, you get this, and then you take small epsilon. So V0 is constant, this is gone after Laplacian, this epsilon cancels this. This term is gone as epsilon tends to 0. And then this part, because we know that overall U is going to be close to a characteristic function times Z. Right? Z is remember that Z is the largest zero of the nonlinearity with parameter S equal to V0. So we have this equation for W. And here we use chi E to denote the characteristic function of the set E. So that's nice. So now we can put two equations together. One is the equation on the boundary of the set, and then there's this another equation on the entire domain D. And these two form a closed system, and we can solve this system. And note that because of the Neumann boundary condition for both U and V, particularly V, so W also satisfies Neumann boundary condition. So if you integrate the left side of the equation, you get a constraint on these two terms. Or in other words, you calculate this, it tells you that the size, the volume of the set E has to be equal to this number, parameter, times the volume of the entire domain. So the size of the size of your set is determined by the parameters of this problem. And there are many parameters, but at this point we can actually put a bunch of parameters together to simplify the form of this equation 8 and rewrite 8 in this more compact form. And over here we only have two parameters now. One is this A, which is just this number, has to be between 0 and 1, and then this gamma, which is positive. So recap. So we have a biological or a physical system on a bounded domain, and now the problem we pose is the following. We are given two parameters. One is between 0 and 1, and the other is positive. And we look for a subset of the set D, such that the volume of this subset is fixed. It's A times the volume of the total domain. And on the boundary of this set, so here I mean the boundary which is inside the D, this equation holds. The mean curvature of the boundary plus gamma parameter times inverse Laplacian inverse with Neumann boundary condition of this characteristic function minus A. And also it's possible that your E, this set E, meets the boundary of the domain. So you could have this situation. So say here is your domain B, and your E can be, well, it can have multiple components. It doesn't have to be connected. So you can have this piece, maybe inside, and maybe more, maybe a circle here, something like that. It is possible that the boundary of E meet the boundary of D. And when the two boundaries meet, so they should form a 90-degree angle. And if you just look at the case where E is entirely inside, then you can overlook this point. But in general, we do allow the two boundaries to meet. So, so that's the equation we end up with. So instead of solving the Tiernan system, which is quite complicated, so at least in this parameter range, we can actually study this geometric problem instead. And another good thing about this geometric problem is that it has a variational structure. You can assign an energy functional to each subset of D like this. And then this equation becomes the Euler Lagrange equation of this energy functional. And here the energy functional is like this, 1 over n. N is the dimension of the space, n minus 1, times the perimeter of E with respect to D. This just means that this is just the size of the boundary of E, which is inside D. Okay, so it's like the surface area. And then gamma over 2 times a non-local quantity, a quadratic non-local quantity. So if you calculate the Euler Lagrange equation of this thing, you're going to get exactly this equation. So that's also a good thing about this model. So the original Tiernan system doesn't have variational structure, but now we do have a variational structure. So there are more tools to use. And even though it's a reduced problem, it's not a simple problem. In one dimension, this problem can be solved completely. We know all solutions of this problem. But in higher dimensions, well, there are some partial results, but it's still far from understanding this problem completely. So today I'm just going to address one issue related to this equation. So we are only going to be interested in one type of solutions, a type of solutions that have the so-called self-organization property. So here is an example of the solutions we hope we can find. And by the way, this problem can also be used to model some physical systems. Actually, it was also used to model Bloch copolymers. So this is a picture, a real experimental picture of a Bloch copolymer. And it's a cross-section. So now it's a two-dimensional problem. And then you want your E, your solution set, to be the union of those little spots. And the question is, can you find a solution like this, a solution that satisfies this equation? Okay, so I'm going to use a theorem of ours to explain the idea behind our approach, and then I'm going to discuss more about our recent results. So this is a theorem which actually tells us how to attack this type of self-organization problem. So let me tell you the theorem first. It's a joint work with Junqian Wei for Chinese University in Hong Kong, and we proved this several years ago. So suppose the domain is a bounded subset of R2, and K is an integer greater than or equal to 2. And we define a parameter rho to replace this A parameter. So define rho this way: K times pi rho squared equals to A times the size of D. And this rho is more convenient than A. So basically, rho is like average radius. If each component of the solution set is a ball and is a disk, and all disks have the same radius, then this rho would be the radius. Okay, so we define this rho as a parameter, and here's the theorem. For every epsilon greater than 0, there is a delta greater than 0 depending on epsilon, k, and the domain only, such that if rho is sufficiently small, or in other words, if A is sufficiently small, and the gamma, the second parameter, is in this range, 1 plus epsilon over rho cube log 1 over rho to 12 minus epsilon over rho cube. If gamma is in this, well, not so narrow parameter range, then we can find a stable solution to the geometric problem. And that stable solution has the k components. And each component is close to a round disk, approximately round disk, not exactly round disk. And the radius of this approximate disk is more or less equal to rho, approximately equal to rho. And if we use theta 1 up to theta k to denote the centers of these disks, and then these thetas must be close to a global minimum of a finite dimensional function. And this function is called f. F is a function of k variables, psi 1 to psi k, and it's defined by the Green's function of the Laplacian operator with Neumann boundary condition. You first do a double sum of Green's function at psi k and psi l, where k is not equal to L. And if k is equal to L, then you use the regular part of Green's function. So this gives us a well-defined function, and then you minimize this function, you find where the centers of these disks are. Okay, so, and then, well, once you have such a theorem, you know how to determine those centers, and you can, well, in some special cases, like suppose your domain D itself is a big disk, and then Green's function is known explicitly, regular part also known, and then you can use MATLAB simple software to minimize that function f, and you will find the location of these centers. So this is a simulation with 100 points, k 100 components, and if you compare this to the experimental data, you see that both have hexagonal pattern. Everybody has 6 neighbors. So here, at least inside, everybody has 6 neighbors. So this is quite satisfactory. Now, how did we prove such a thing? Well, I'm not going to explain the entire proof, but one central idea is that when you have a multi-component solution, you can first study a single piece, a single component, and you can first ignore the interaction between different components. So basically, you need a profile problem to a single component. And in PDE's theory, sometimes we call them ground state problem. So here we also have a ground state. So you first study that problem, and then if you know enough about your solution to that problem, and then you can put your solution, you call it Ansatz, into a bounded domain, and then you study the interaction between different components, and in order to complete the proof of our theorem, the proof to the existence of a self-organizing pattern. So the important thing is first to identify a profile problem, and then try to find a solution to that profile problem. And such a component, a solution to the profile problem, I call an Ansatz. And when you look at the profile problem, well, you don't really have to worry about the component-to-component interaction. You just have to worry about the self-interaction between the component and itself. Okay, so here's the profile problem. And this is the problem I will be talking about today. So it's a problem defined in the entire space Rn. And again, you are giving 2 parameters, n positive, gamma also positive, and you are looking for a set, a subset E of Rn, and a number lambda, such that the volume of the set is fixed, is equal to n. And on the boundary of the set, this equation holds. This equation says that the mean curvature of the boundary of the set plus gamma, the parameter, times this n of E. And these 2 numbers add up for constant lambda for all points on the boundary of this set. And this n of E is simply the Newtonian potential of the set. So in 2 dimensions, Newtonian potential is calculated by this formula, 1 over 2 pi log, and n equal to 3, then this is the Newtonian potential. So every time you have set E, n E is a function on R3. And then you look at this function now on the boundary of E, and you add it to the mean curvature of the boundary of E, and you hope that these two numbers add up to a constant throughout the boundary of E. So this is my problem of mean curvature and the Newtonian potential, or I call it the curvature potential problem. And this problem itself also has a variational structure. So it's like this. You have the perimeter term, and now this time the perimeter is just a perimeter, not against a set. This is a perimeter in Rn. And then the Newtonian potential itself is integrated over the set E, because the Newtonian potential is a function, so it's integrated on E. And one good thing or bad thing about this problem is that even though you start with 2 parameters, m and gamma, you can always change the space variable x, make this big or large, to eliminate the 1 parameter. You can always assume that n is equal to, say, 1 or any other convenient number. So you actually only have 1 parameter to play with in this problem. This is also kind of bad news, because it makes the problem a little more difficult. Okay, so we have found a number of solutions to this curvature potential equation. So here I plotted some of the solutions we know. So in 2 dimensions, there's the disk, and this exists for all gamma. And then for some gamma close to 12, there is a oval, this egg-like solution. And then there's also kind of a ring solution if gamma is sufficiently large. So in 3 dimensions, we know a ball is a solution. And also, we also have a shell solution. The shell is just 1 ball minus another ball. So the center, this core is hollow. And then we also have a torus, a donut-like solution in 3 dimensions. So let's see how many I can cover today. Okay, so the disk, let's look at 2-dimensional case. Why is the disk a solution? Well, this is very easy. So for this disk, the volume, the area is equal to pi. And on the boundary, now it's curvature, now I mean curvature is constant. And the disk is radially symmetric, so the Newtonian potential is also radially symmetric. So on the boundary, again, this is a constant. So the sum of 2 constants is equal to constant. So this is trivially satisfied. So that's easy. Less trivial is about the stability of this solution disk. And we can actually prove, this is not too difficult, but you have to use some trigonometric series to prove that if gamma is small, between 0 and 12, then this disk is a stable solution. And if gamma is bigger than 12, then this disk becomes an unstable solution. And once we know the stability property of the disk, we'll be able to prove our first theory. So as an application of this disk ansatz, we can use this disk ansatz. We first take the ansatz and scale it down, shrink it, make it small, and then take multiple copies of the small disk and put all these copies in a bounded domain. And then we need to make some small perturbation to each small disk. So now in order to have this problem satisfied on the bounded domain, we cannot use the 100% perfect disk. We have to make some perturbation to the boundary of disk. And we also have to put the disk in the right place. And then if you do these things properly, you find a solution to this original problem on the bounded domain. So this is the general idea. So you first study the profile problem, and then you do these tricks and end up with a problem with a more or less a periodic pattern. Yes. Stability. It's a stable. Yeah, that's a good question, because you have to is the stability in a particular sense. So you take, so for example, in this case, right? So you take a disk, and then you perturb the disk by a 2 pi periodic function, perturb the boundary of the disk. With respect to that perturbation, it's stable up to translation. So yeah, and of course, there's the issue of norm metric space, but so a simple way to say it is just the stability with respect to that type of perturbation. So, and you can also make it more complicated to use a more coarse norm, and then stability becomes more complicated. So, but here we use a very fine norm, so C2 perturbation to the boundary, and stability in that sense. Up to translation, you can always move this thing. And the solution we found that for this problem is also stable in that sense. Okay, so, well, that was the first ansatz, this ansatz which exists for all gamma. And the second ansatz we did, this is a problem I did with Xiaofeng Ren of Wuhan University. We were interested in, yeah, so here the pictures are not so good. Another pattern, and this pattern, rings on the, let's see, on this, this is a freshwater ray, also a fish. And you see this like a ring inside, the color is lighter, and then around it you have darker color, and then outside again you have lighter color. So a ring is, well, two-dimensional ring, something like this. And the theorem here is that, again, you look at the curvature potential equation in R2. Now, it turns out there is a critical number gamma 0, such that if gamma is greater than gamma 0, then this equation has a solution of this ring shape, if and only if. And this solution exists if gamma is sufficiently large. And also, there's another gamma 1, which is greater than gamma 0, such that if your gamma, this gamma is bigger than the larger gamma is greater than gamma 1, then you have a stable solution. And if your gamma is between gamma 0 and gamma 1, you have an unstable solution. Now, you may find this thing not very intuitive, because if you compare it with the earlier stability result, what I said was that in the Bohr case, your solution is stable if gamma is small. But now in the ring case, our solution is stable if gamma is large. Why is that? And the reason is that, well, the thing is that when you look at the Bohr case, or look at the disk case, the disk has fixed the radius for any gamma. But in this ring case, the radii, the inner radius depends on gamma. When gamma changes, the shape of this ring also changes. Actually, when gamma gets bigger, this ring also gets bigger, also thinner. And therefore, you know, there's a balance between larger gamma and the shape of this set. And it turns out actually it's better to have a large thin ring to have stability. So, and once we know the stability of this thing, and then again we can play the same trick to prove existence of existence to the problem on the bounded domain with multiple components. And in this case, we can find a solution like this. So this is the solution set where each component is a ring. And you can also find a solution where some components are rings and some components are disks. And this again is a joint work with Kang. So, okay, so now let's move to 3 dimensions. What do we have in 3 dimensions? Obviously, there's a analogy of disk. You can look at the ball of radius 1. This is also a solution, and you can also prove that this thing is stable if gamma is less than 12 or less than 15 now. And then you can use this ball as an ansatz, as a building block, to build a solution of multiple small balls in a bounded domain. And again, you have to make rho small. Rho is now the average radius. And the gamma has to be in actually, this is a smaller parameter range, 1.5 over rho cube and 15 over rho cube. These two numbers are of the same order. So in 3 dimensions, it's actually, it's more difficult to find a solution. And again, the location of these small balls can be found by minimizing the same function. Okay, so that's the first one. And then naturally you would think that, well, let's look at the 3-dimensional analogy of ring. So that analogy would be a shield. You take a big ball and you subtract a smaller ball. So this is called a shield. And this guy is a solution if gamma is sufficiently large. But the bad news is that this guy is always unstable. So in 3 dimensions, you know, the obvious, the naive analogy of ring is not really stable. So this is not too good. So this is not the thing you want to use to model real problems. Now, what do we have? What else do we have in 3 dimensions except these two ansatz? So it looks that there's another structure which is quite popular in 3 dimensions. And it appears in various problems. In fluid mechanics, people study something called the vortex ring. And in quantum mechanics, people also study something called the vortex ring. But of course, vortex rings here now it has never been proved, should come from some things like Bose-Einstein models. And also, in philosophical polymer theory, rather recently, people have also observed this kind of toroidal tube structures. So a toroidal tube structure, the structure here I'm talking about is this. So it's a set of many components, and each component is like a donut. It's like a torus. And so this is the picture I'm interested in. And so here's our more recent theorem. So again, we look at the curvature potential equation in R3, and we can find a set which looks like this, a tube, a torus. And the volume of this is equal to 1, and this solution exists if gamma is sufficiently large. And okay, so we can also say something about the 2 radii of this torus. Well, it's not exactly torus, it's a perturbed torus, but still, we can define a number f, which depends on gamma, f of gamma, by this formula, by its inverse. And this f tends to 0 as gamma tends to infinity. And then let p and q be the 2 radii of the torus of this solution, where p is the bigger radius, q is the smaller radius. Then the volume is equal to 1, this is the volume. And then we know that q is like f of gamma. Asymptotically, we know what q is. And p is like 1 over f squared. So q is like f, small q, small cross section, and p is 1 over f squared. It's a larger radius. So that's the shape of our solution. Okay, so that's one solution we know. And more recently, we also found a second solution to this curvature potential equation. Now, actually, the more we study this problem, the less we know about the structure of the energy function or the structure of the solution set. So actually, this problem, even though it looks quite simple, it can have a complicated solution. So like this solution, where you have 2 tori, an outside tori and an inside tori. And together, the union of these 2 sets still satisfy that equation, curvature potential equation in R3. And for this solution, we know that, okay, so let P1 and Q1 be the two radii of the inner torus, the inside the torus, where Q1 is the cross-section radius, P1 is the other radius. And P2 and Q2 be the two radii of the outer torus. And the cross-section, Q1 and Q2, both are close to f of gamma, the same f of gamma. But the p's are, of course, different. They are of order 1 over f squared, but the one is bigger than the other. So asymptotically, we know that p is equal to 1 over f squared times 2 pi squared times a number pi 1 or pi 2, depending on which torus you're looking at. And these two pi's are determined, again, from a function. And this function is from P1, P2 to this quantity. Okay, in this quantity, you have this g function and then this g1 function. So what is g function? G function basically is the Newtonian potential, the kernel of Newtonian potential written in the cylindrical coordinates. You assume that everything is axisymmetric, and then in the cylindrical coordinates, the Newtonian potential, the fundamental solution, can be written this way, where Rz is the distance to the z-axis, and z is the z-axis, st. So this is the Green's function, g. And the leading order singularity of Green's function is still like this, like log. And g1 is the next order term. Although in this case, g1 is not smooth. g1 is only c alpha. But anyway, so this is g1, where your p, where you have p1, p1, p2, p2, and then you have when you have p1 and p2. Different p's, you use g. So take this function and you can minimize this function to find pi 1 and pi 2. And these pi 1 and pi 2 give you the asymptotic value of the radii of the two torus. So that's the second solution. Well, the second torus-related solution. Now here's a third solution that I found recently with the Xinbin Pan of East China Normal University. Again, we look at this problem in R3 of volume 1 now, and we found that you can actually build a solution also of two components. And one component has one component is a torus outside, and the second component is a ball, a small ball inside. So something like this. Well, of course, not the exact ball, but approximately ball and an approximate torus. And the union of these two can also satisfy that equation in R3. And for this solution, we let L be the radius of the ball, P and Q be the two radii of the torus. Then, of course, because the volume is equal to 1, so this equation holds. And also, we find that L is approximately equal to that same f of gamma times 2/3 of f gamma, and the Q is approximately equal to f of gamma. So the area of the cross section of the torus, I mean the radius of the ball is about 2/3 the radius of the cross section of the torus. So this equation also exists. And what else I want to say? Okay, stability. Now, how about the stability of these three torus-related solutions? So I mentioned the three, right? A torus, a single torus, a double tori, a bigger torus and a smaller torus, and a ball torus, a ball inside and torus. So unfortunately, I don't have a complete answer. Well, this part is missing. And the thing is that when you look at these three objects, all of them have two symmetries. One is the axis symmetry around the z-axis, rotational symmetry. And they also have the Miller symmetry about the xy plane. Now, if you just look at the stability among all sets without symmetry, then unfortunately, I don't know whether the torus is stable or not. So this looks like a complicated problem, and the computation is quite tedious to study this problem. But if you just look at sets that are axisymmetric, restrict yourself to that smaller class of sets, then the torus is stable. And if you further restrict yourself to sets that are both axisymmetric and mirror symmetric, then of course this is also going to be stable. And in the second case, for double tori, in general it's not stable. And even if you impose axisymmetry, this guy again is unstable. But if you impose both axisymmetry and mirror symmetry, and then this will become stable for the double torus. And for the third solution, void torus is not stable in all these classes. So this gives us some idea about the complexity of this problem, the problem of curvature and Newtonian potential. And I think there's still a lot to be done in this area. And after all, we started with a PDE system. We look at one small parameter, one particular parameter range, and we derived a geometric problem. And that geometric problem is complicated. In order to solve that, we have to identify a profile problem, right? Ground state problem. And even for the ground state problem, we already found so many solutions. So let me just stop here. So if you are interested in this area, I think there's still a lot of things to do. Thank you.